Good. Give me a thumbs up so I can move on to the next one. Excellent. Now, what if instead of having a line of charge, what if I actually had a sheet of charge? So my sheet of charge will look something like this. And let's suppose I choose it to be a positive charge that's everywhere. Now, what kind of symmetry would make the most sense in this case? And suppose I'm being asked to find the E field at this point. Well, can I draw tiny pillboxes and then add them all up? And that might be the Gaussian surface I'm looking for. So one has to go up and the other one has to go down.
Dr. Zane, I'm not understanding your orange square
Okay.
thing right now. I'm a little confused.
Okay. So draw So imagine if this is your sheet. Yeah, this is your sheet. And I'm trying to draw a box on top of this sheet. And then the same box to be at the bottom of the sheet. Okay? Oh, actually, this is a better sheet. This is a better example. This sheet. Okay, and then imagine it again on both sides, right? It can't be on one side, so it has to be on both sides. Okay, so so do we understand the Gaussian surface? And again, it has to be bigger, right, to enclose the actual point that we're looking for. Right, draw it big. And the same surface down. How will I write the Gauss's law for this case? If the area, well, what side matters in this case for the Gaussian surface? Do the sides matter? No.
The vertical surfaces?
The vertical surface is the only one that matters. Very good. So now my dA will go this way, right? That means, may I write my Gaussian surface as and for a Gaussian surface that extends all the way over the sheet, may I just simply write this as EA, sigma A over epsilon naught. Do you see why it became sigma A? Where it's surface charge density. A's go away, and I am left with so the E field due to a sheet of charge is just sigma over epsilon naught. So I'm going to build on these sheets now. Okay, what if instead of one sheet of charge, you had two sheets of charge? And in that case, we call them parallel plates. Okay, what do they look like? So I'm just going to draw the cross-sectional area, okay? So imagine there's a huge sheet behind it. So I'm just showing you how would you say that? Like a sidle, like the thickness, okay? So they will look like this.
Could you say the width?
The width, yeah, not the width, the thickness. So the width would be, like, imagine these sheets are like this. Do you see what I'm saying? Like, this is the length, this is the width, but we're looking at the thickness of them. Like, just this lateral view. So I want to make sure that we understand that. It's like these two views, and I want to show you the E field in the middle. So if this is plus, and this is minus, what is the E field due to plate 1? Plate or sheet? Can I call it plate 1? And what is the E due to plate 2? Yeah? Picking it up from the one before. Now, what will the E field look like between these plates? They look like this, right? So now let's talk about this. E left, E center, and E right. What is the E field at the left side? As long as both charges are equal, when sigma 1 equals sigma 2, what is E to the right? And what is E at the center? Note, I'm talking about their magnitudes, right? So I'm going to ignore the plus and the minus. Actually, even if I don't, even if you think about it, the plus is going this way and the minus is also going this way. So then what you have to do is sigma over 2 epsilon naught plus sigma over 2 epsilon naught gives you sigma over epsilon naught. Oh, and by the way, so EC will just be sigma over epsilon naught. And what is E inside? So what if I asked you, what is the E field at this point? Inside the field. At this point, like let me call it E1. What is the electric field inside the conductor? Remember, charge resides only on the surface of the conductor. Inside, it will be 0. What is the E field at this point, E2? Inside the negative, 0 again. Very good. Okay, so E1 will be 0 and E2 will be 0. And this only holds for when sigma 1 is equal to sigma 2. When sigma 1 is not equal sigma 2, so this was case 1. For case 2, when sigma 1 is not equal sigma 2, how do these values change? In this case, what you will have to do is imagine this is plus and this is minus. I'm going to draw the blue for plus, okay? So plus is always giving out. Minus is always pulling towards. So E minus will also pull away and towards. So then you will have three different situations. This will be E plus L, E plus center, E plus right. And this would be E minus left, E minus center, and E minus right. Oh, this should be closed. Okay, so then you'll have to do sums at each level. And then the plus and minus will become important. Remember I was talking about this? So two portions of large sheets with uniform surface charge densities of plus 6 microcoulombs and minus 4.3 coulombs per meter squared, microcoulombs per meter squared. Find the electric fields to the left, the center, and the right. How would you do that? So go back to the picture we drew and draw the arrows of what it would look like. So I'm going to move this picture in the middle and move this slightly away. Center this. So what will the positive fields look like? E plus, E plus, and E plus. What will the negative ones look like? Well, coming in, coming in, coming in. E minus, E minus, E minus. So what will EL be? And remember, forces add, so fields also add. It's called the principle of superposition. So what will be EL? Choose coordinate axes. Which ones do you want? Normal? Minus E plus E minus. What would EC be? E plus E minus. And then what would ER be? And then it's just a matter of plugging numbers in. Yeah? This gives me charge densities. So I have to convert the charge densities into E fields. How will I do that? These are sheets, right? So I have to do one for E plus and I have to do one for E minus. Once you have your E fields, then it's just a matter of plugging numbers in.